Question 12 says, what period 3 element is described by the following ionization energies? So ionization energy, specifically the first ionization energy of something is the energy to take away the first electron. So if we have element X in the gas phase, it's going to yield X plus in the gas phase plus an electron. Okay, it's the energy required to take away an electron. Electron affinity is the opposite. Electron affinity would be to add an electron to an element in the gas phase. But we could take away more than one electron. We can look at IE2, which is X plus in the gas phase yields X2 plus in the gas phase plus another electron. And we could take away another electron, IE3, which is X2 plus in the gas phase yields X3 plus in the gas phase plus another electron. And we could theoretically go on until we took all the electrons away from X. But what we're given here is not what is the definition of ionization energy. What we're given here is specific ionization energies. So to take away the first electron takes around 1,000 kilojoules per mole. To take away the second takes around 2,000. It makes sense that taking away the second is going to be harder because now it's already positively charged and we're trying to take away another electron. The third one is harder still. The fourth one, harder still, each one going up by somewhere around 1,000. Then the fifth one, harder still. But what you'll notice is this giant gap between the fifth one and the sixth one. And this is because this species has 5 valence electrons. When you try to take away the sixth electron, it takes a very massive amount of energy. So the period 3 element with 5 valence electrons is actually phosphorus. So when you take away, because it's in group 5A, when you take away 1 electron from phosphorus, it's isoelectronic with silicon, and that costs you about 1,000 kilojoules per mole. When you take away a second, it costs you around 2,000 kilojoules per mole, and it's isoelectronic with aluminum. When you take away the third, it's isoelectronic with magnesium, and it costs you around 3,000 kilojoules per mole. When you take away the fourth, it's isoelectronic with sodium, and it costs you around 5,000 kilojoules per mole. When you take away the fifth, it's isoelectronic with a noble gas neon, and it costs you around 6,000 kilojoules per mole. Now you've taken away all of its valence electrons, and it's isoelectronic with the noble gas. If you want to take away another electron, it now costs you roughly 4 times as much energy as this one to take away that next one, because now it's isoelectronic with the noble gas. So generally speaking, when you see this large gap, okay, when it goes up by about 1,000 each time, about 2,000, progressively taking more because you're taking away from something that's progressively more and more positively charged. But when it becomes isoelectronic with a noble gas, it takes a massive amount of energy. So since the sixth electron takes a massive amount of energy, it must have had 5 valence electrons. So the period 3 element with 5 valence electrons is phosphorus, choice letter